Hello everyone. In this video, we will be discussing clock synchronization in distributed systems. Let's get started. Computers use quartz. Quartz is nothing but silicon dioxide, SiO2. So computers use quartz clock to track time, which runs even when power is off. Quartz is a piezoelectric crystal that vibrates at a fixed frequency. So two terms. One is piezoelectric and second is vibrates at fixed frequency. The first term, piezoelectric, means any substance that generates electricity whenever we apply mechanical stress to it. For example, in Japan, I have seen that some of the roads are made of piezoelectric material. So when people pass by on that road or some vehicle passes by, then it starts generating electricity. So quartz is such a substance which is piezoelectric. And this crystal vibrates at a fixed frequency, and thus we can actually use this to make clocks. Now, clock error gradually increases due to clock drift. This drift can happen due to temperature, speed, or pressure. So, if you buy a clock today, and let's say it is made up of quartz, you will see eventually after a couple of years, this clock will start showing wrong time. Even though the battery is there, the quality of the clock is very high, but you will see there will be an error which will be gradually increasing with time. Why is that so? This is called as clock drift, and this drift occurs because of temperature. Speed, you know that from Einstein's special relativity, if speed increases then time slows down. So if you travel a lot, then your time might lag behind. Or pressure, let's say you go somewhat below sea, or you go to climbing or hiking, then there is a difference between pressure, and thus due to temperature, speed and pressure, the clock errors increase. The difference between two clocks at a given point in time is called clock skew. So this is represented as a theta. So this is skew, clock skew. Now, one more term is tick rate. So it is equal to the number of ticks or pulses per unit of time. For example, a clock with a tick rate of 1 Hertz ticks once per second. So you know that 1 Hertz, we used to have this measuring unit when we studied sound, right, in schools and colleges. So Hertz is nothing, something which is happening in per second basis. So 1 Hertz means this ticks once per second. That's called a tick rate. Now, these were the terminologies. So, what is clock synchronization, which we are discussing in this video? Clock synchronization basically aims at minimizing the clock skew, which is theta, as much as possible. Nothing is perfect. We might not be guaranteeing that the clock skew is 0. But we will say that it can be reduced to almost 0 if we go through some of the precautions. So, let's discuss those. So you got the concept, the tick rate, the clock drift, and then clock synchronization. So let's move forward. Periodically sync times from a central server which has more accurate clock, say atomic clock or GPS receiver, using NTP, which is network transfer protocol, or PTP, which is precision time protocol. That means if we know that our clock might not be accurate, so let's say your quartz clock is not accurate, that you know that after a couple of years this clock is either falling behind the current time or is fast enough showing a future time, then you can periodically sync it with a more accurate clock. Let's say it is hosted somewhere in India or somewhere in, let's say, some US location. So you are periodically syncing it there using some protocols called as NTP, which is network transfer protocol, or PTP, which is precision time protocols. It uses the fact that atoms oscillate at high and very precise rate, and thus they also eliminate errors due to manufacturing defects. So we just understood that manufacturing process itself can introduce defects, because let's say there was some dusting, right? There was some dust. So if you have seen a very good web series which is known as Made in India, a Titan story. So it is the story of the company Titan by Tata. Now, when JRD Tata was wearing the first Titan watch, you will see in the web series that their time was lagging behind, which was not accurate. This is known as clock drift. This issue was occurring because of clock drift, and we can remediate that with the help of NTP or PTP. So you see, this is a screenshot I have captured from my device, that in my datetime settings, you will see that the source of this time will be Apple server. I have not manually set it up. So it is automatically set. This toggle button is on. So you will see the server is Apple, time.apple.com, and my computer is picking up time from their server, which is having a much accurate clock. So you got the point? Even if your device has the potential to show inaccurate time, you can rely on a more accurate server to sync the time to your device. So that's the crux. Now let us understand this with the help of a diagram. So let's say you are the client. You are wearing your watch. Now at time t1, your device sends a request that, hey, NTP server, network time protocol server, I want to get the latest time. Okay, so at t1 this request goes, and since there is a network delay in the system, let's say time t2 the request was received by the server. Now server will be handling a lot of requests and might be doing some processing as well, some logging. So at t3 it sends the response back to the client, your watch, that okay, this is the time which at this moment is the accurate one. And this response again goes through the network, which is internet cables and all deep down the sea. So it is having latency as well. So at t4, let's say you received this response. So at t1 you sent the request, at t4 you received it. So what is the round trip network delay? So this delay we represent as delta. So how do we get the round trip network delay? How much was the network delay? It is simply how much time did the data, the request or response, is spent over the network. So that is nothing but t4 minus t3. This is the response time, plus t2 minus t1, which is what? The time taken by the request to reach from client to server, and this is the time for response to reach from server to client. So this is for response and this is for request, and this is called as delta, which is the network delay. If we can rewrite this as t4 minus t1 minus t3 minus t2, and this is the same equation. So just remember now that round trip network delay delta will be having this formula. Now let's proceed. So here network delay is equal to time response received minus time request sent. Response received minus time request sent minus server processing time. So T3 minus T2 is what? Server processing time. This time we discussed, right? This is the server processing time. So this is the formula of network delay delta. Now, and T3 minus T2 is the server processing time, and T2 being the time server received the request, and T3 being the time server sent the response. Now, if we assume that the network delay is symmetric, that means client to server and server to client take the same time. It might be that from client to server there are faster cables, and from server to clients there are slower cables, older cables. Then network will be asymmetric, network delay will be asymmetric. But for the sake of simplicity, let's assume that it is uniform. That means client to server and server to client network delay is same. Then T4 is equal to time server sent the request plus network delay. Hence T4 is equals to T3 plus delta by 2, because we say that the delay is symmetric. So if delta is the total network delay, then delta by 2 was spent for the request and delta by 2 was spent by the response. So then if at T3 server sent the response and at T4 the response was received by the client, that means T4 is what? T3 and the network delay, which is delta by 2. So this is the formula. T3 plus delta by 2. Now, what will be the formula for clock skew? So we discussed about that clock skew is represented as theta, correct? Now, theta will be, what was the formula we derived above? So theta, we said that theta is the clock skew, and the clock skew will be T3 plus delta by 2, which is the time the server reported the correct time, and then this time was added by the network delay. When this response reached the client was running on T4 time. This was the local client time, and this will become the time server is saying the correct time. So what should be the clock skew? It will be the difference between these two. So T3 plus delta by 2 minus T4. Now let's put the values. So T3 plus, what was the delta? Delta we derived as this one. So let's put the values. T4 minus T1 minus T3 minus T2 by 2 and minus T4. Let's simplify this. So it will become T3 plus T4 by 2 minus T1 by 2 minus T3 by 2 plus T2 by 2 minus T4, which is nothing but T3 minus T4. This will become T3 by 2, this will become minus T4 by 2 minus T1 by 2 plus T2 by 2. If I take 1 by 2 common, then this will become T3 minus T4 plus T2 minus T1 by 2, which is this, the exact expression. So you got the idea, right? Theta will be this, the clock skew formula. Now, client should query the server frequently so that theta is never too large. If your client, which is considered the watch or the computer, is querying the accurate server very often, let's say every 1 minute or every 5 minutes, then obviously they will be getting latest time. So theta, which is the clock skew, will be never too large. That means your local time, the client time, will be more or less accurate. Now, let's come to one interesting fact. Do you see any issue with this code? Long start time is equal to system.currentTime in milliseconds. By the way, this code is in Java, but understand the concept. Then we do something, that means it is a processing phase. It is doing something, the server is doing something. Then long end time becomes equal to system.currentTime milliseconds. Now these three statements, and at the last we are directly subtracting end time minus start time. So anyone who is a beginner in the computer science will say that, okay, end time minus start time, we will get the processing time, correct? But what if the network time protocol, which is client requesting the server to get a more accurate clock, let's say start time was 100, but server was actually running at 95. So when the client is querying server, let's say server is doing some processing and also NTP resets the clock of the server. So now the end time will become 95 plus or minus something, right? So if you do end time minus start time, what it will become? Approximately 95 minus 100, which is minus 5. Can time be negative? Can the processing time be negative? It will at least be 0, right? If it is not doing any processing. How come it can be negative? This is because the system.currentTime in milliseconds is not monotonic. It is not guaranteed that it will always keep increasing. NTP can come and reset this clock at any moment. Thus, in production, I always put a comment on the PR that never use this pattern. This is a very wrong pattern when you do end time minus start time. There is nothing wrong with current time in millisecond. Use it. But don't use this method to find the processing time. So the problem with current time in milliseconds is that it is time of the day clock, which can suddenly jump drastically forward or backward during NTP stepping. The same thing we discussed just now. Instead, what should we do? Use nanoTime, which is designed for these cases where client may sync with the server using NTP while measuring runtimes. NanoTime is a monotonic clock. So monotonic means it is always strictly increasing. Not increasing, strictly increasing. So if someone says that, is this increasing sequence? You can say that it is increasing. But is it strictly increasing? No, because the two elements are same. Now, is this increasing? Yes, it is increasing. Is it strictly increasing? Yes, it is strictly increasing, because every next element is bigger than the previous one. So what is a good pattern to have is use system.nanotime and then find the processing time by end time minus start time. This will always give the correct time. Now let's come to the last topic, which is vector clock, also known as version vectors, versus Lamport timestamps in message ordering. So there are two concepts. Whenever you send any message on WhatsApp, you can use vector clocks, also known as version vectors, or Lamport timestamps. So what's the difference between these two? Lamport's logical clock is a procedure to determine the order of events. In what order did the events occur? It provides a basis for vector clock algorithm. Due to the absence of a global clock in a distributed system, Lamport's logical clock is needed. We just discussed above that there is an absence of global clock because client might be running behind or forward the time at which server is running. So there is not a global clock. Client has to frequently query the server, and server itself depends on itself with a more accurate clock. So it is not a precise clock, but it is more accurate as compared to client. So there is a absence of a global clock in a distributed system. So both are logical clocks, vector clocks as well as Lamport timestamps. That is, they capture chronological or causal relationships. We will come to causal relationships in the next videos. But for now, understand that chronicle or causal relationships is basically establishment between two events, which events led to which events, basically establishing the relationship between these events orders. So for both clocks, we can assert that if A happens before B, then clock of A will always be less than clock of B. So if we say that A happened, then B happened, then we say that clock of A will always be strictly less than clock of B. Vector clocks allow to determine if any two arbitrarily selected events are causally dependent or concurrent. So if they are not causally dependent, then they are called as concurrent events. We will discuss this in more detail in an upcoming video. Lamport timestamps cannot do this. So vector clocks allow us to determine if we select any two events, were they causally dependent or they were concurrent. Lamport's timestamps cannot do that. So if we say that A happens before B, then we will say that vector clock of A is less than vector clock of B, the same concept we discussed here. But the reverse is also true. So with vector clocks, you can also say that if the timestamp of A is less than the timestamp of B, then you can certainly say that A happened before B. Now, Lamport timestamps are more compact. Vector clocks require overhead proportional to the number of nodes. Let's say in a distributed systems you are having 10 nodes, 10 servers. Then vector clock size will be proportional to 10 because you will be maintaining an array. So for example, if we have 3 node system, the vector clock will look like T1, T2, T3, where T1 is the logical time of node T1, node 1, then T2 is the logical time of node 2, and T3 is the logical time of node 3. Got it? So you maintain an array which is having time of each server, each node. When a node boots up, it determines the number of nodes in the system and fills an array of size n with zeros. Before executing an event, the node increments the clock of that node's time in the list. So it will just do an increment n of I plus plus before executing any event. The main problem with vector clocks is that they require a large amount of storage because each node must store n timestamps based on the number of nodes. So let's say 3 nodes are there. Each node will be having the time of itself and the other servers. So the first node will be having an array of size 3. Second will be also having an array of size 3. And third one will also be having an array of size 3 representing the timestamps of the servers. So in this video, we discussed lot of things, including why clock errors happen, what is tick rate, what is meant by clock skew, what is clock synchronization, what NTP is and what PTP is, with a practical example from MacBook. Then we derived some of the formulae. For example, the formulae for clock skew. We saw an interesting fact why we should never use current time milliseconds to calculate the time elapsed, and instead we should use nanotime. Then we discussed the difference between vector clocks and Lamport timestamps. If you liked the video, please consider sharing and subscribing to the channel. If you have any topic in mind which you are finding difficult to understand or would like me to create a video of it, then please feel free to comment and I will take a look at that. Thank you so much.